Hello, everyone. Welcome to the 2026 J Champions Conference. And the conference is now going to begin with Thomas Vitelli. And sorry, I guess my thing is, let me close my other thing. But yeah, so welcome again. And Thomas is based in Italy. And this is very nice. He's going to be talking about modular RAG, Retrieval-Augmented Generation architectures with Java and Spring AI. So here's Thomas, and we welcome him. So the stage is yours, Thomas.
Thanks so much, Mary, and thank you all for joining this session. Now, it's been a few years that we've been building AI applications, integrating our standard enterprise Java applications with generative AI capabilities. And we realized pretty quickly that large language models, of course, can be useful to answer questions based on the data the model was trained on. But whenever we need to ask questions about novel data, perhaps about current events or about our own documents, perhaps our company documentations, then models, of course, don't have any way to get access to the data or access to any other parts of our system. So today I want to talk about how we can provide contextual information to a large language model so that together we can build an application that can combine the power of large language models with application capabilities or in order to retrieve relevant contextual information and connecting the large language models both to our data and our APIs in our systems. You heard I'm Thomas Vitale. I come from Italy. I'm based in Denmark now. I work at a company called Systematic. I'm really passionate about anything Java and cloud native related. Also, big supporter of open source projects. I contribute to different projects, and some of them we'll use today. I also wrote a book about cloud native development with Spring Boot a few years ago, and right now I'm working on a new book together with my friend Mauricio Salatino with tentative title Developer Experience on Kubernetes. But let's get started right away. It will be a very practical session. We're going to work with the standard Spring Boot application. That will be our foundation. On top of that, we add a few extra ingredients. The first one is Spring AI. That's the library in the Spring ecosystem that lets you integrate your Spring Boot application with large language models. So it's a key part of our architecture. Then I also using Vaadin. Vaadin is a great framework to build full stack Java applications. I'm mostly working on backend. I'm not very comfortable writing JavaScript, and Vaadin lets me build very nice UIs using pure Java. So I really love it for that. And then the final ingredient is a framework called Arconia. It's an open source project that I started, and it's an add-on for extending your Spring Boot application with additional features. And we'll see in a minute what kind of features we're talking about. But our application will not work in isolation, of course. The first thing we need to integrate is an inference service, because, of course, we want to consume large language models. There are different options for that. For example, we can use something on premises or something in the cloud. Everything I'll be running today, with one exception, is running purely locally on my local development environment. I'm using Ollama as the inference service. It's an open source project. But in the same way, you can pour the same code through different cloud inference services because Spring AI provides very convenient abstraction. So for example, I can easily switch to Mistral AI. That's a great European platform that I like to use because they also offer their models as open source. So I can run the same models both locally with Ollama and in the cloud with their platform. That's, of course, an important part. But most applications will also need to store some data, and our applications will also need that. So I will integrate a database. I'm going to use PostgreSQL. Then, since I mentioned earlier, I want to integrate large language models with both my data and my APIs. I need some kind of way to process and prepare data for scenarios involving large language models. For doing that, I'm going to use an open source project called Docling. So we'll also integrate our application with that. And finally, we also want to get some observability capabilities here. Now, in general, whenever we build applications, we think about observability very late in the process, when we are almost to production, or sometimes even after we deploy our applications in production. I'm a firm believer that observability already belongs in a development environment. it provides so many great benefits. Even more so when we're talking about AI applications, because there's so many things happening under the hood whenever we communicate with different services that without having observability capabilities already in our development environments, it becomes pretty hard in order to troubleshoot and to implement the feature that we want to implement in the best way, because we don't have the necessary visibility into what's happening under the hood when we call a large language model. All right. Now, based on this, we have a Spring Boot application. I need to integrate these services. There are different ways for doing that. So I could write some Docker Compose configuration. I could write some test containers code, but I'm lazy, so I don't want to write any extra code or extra configuration. That's why I'm going to use the Arconia Dev Services. This is a way to have your application automatically provision all the external services you need as part of your application lifecycle. So whenever you are in development mode, iterating and building new features, or whenever you're running automated testing, you can add a dev service dependency for each of the service you need, and that will be managed automatically whenever you start a Spring Boot application. So you can run it normally from Gradle, from Maven, from your IDE, and there's zero code and zero configuration needed for this. This is one of the features that I implemented in Arconia. The inspiration comes from Quarkus, that has this very nice concept of dev services, and the implementation is based on test containers. All right. I have my application up and running. Let's have a look at it. So it's a very simple chatbot. Let's give it a try. This is the JChampions conference. So maybe we can ask a question about when is JChampions conference taking place? Let's ask the question. As I said, I'm using Ollama, so everything is being processed locally. And that's it. The model doesn't really know how to answer. And that makes sense, right? Because the model that I'm using is not aware of current events. It doesn't have access to external systems to retrieve the necessary information to answer my question. So in the best case scenario, like in this case, the model tells me that there's something wrong, maybe double check your question. But very often the model will just hallucinate. So it will just make up an answer that sounds very confident, that sounds reasonable, but it's wrong. So the first problem that we are facing here is how to extend the capabilities of the model in order to be able to determine information that were not part of the original training set. So if I want to answer this question, what would I do as a human user? I would probably go to some web search engine. I would search for JChampions Conference 2026. I would find the website, and here I would get my answer. The conference is starting today, but the model doesn't have access to this. So if I want the model to give me an answer based on this information, a simple way of solving that is copying all of this, going back to my application, and now I can ask, consider this context, and I paste all that text from the website, and then I can ask, when is the JChampions conference taking place in 2026? So I'm providing both the question and additional information the model can use to answer. This pattern is called prompt stuffing, like this. So what happens is that we don't only ask a question, but we also provide the additional context. Now, this works, but of course it's not ideal, it's not scalable, and especially like in this case, if I already have the answer, it doesn't make sense to ask the question again. So we want to automate this process. First, though, I want to show you what's happening under the hood. So we have a baseline. I told you that I wanted observability as part of my local development environment. And in this case, I'm using Phoenix. Phoenix is an open source AI observability platform that is also being provisioned by my Spring Boot application, thanks to the dev services. So we can see that I'm using in the code a Spring AI chat client. I'm passing the input, so you can see all the inputs here. There's the question and the additional context. I'm using Ollama, and here are the full trace of what happened. So I send a chat request using a model called Granite 4 from IBM. It's running locally in Llama. I can see the answer. I can also get additional metadata about this interaction. For example, how many tokens I consumed in order to send my question and get an answer. Now, this is not very relevant when running locally, though it can have two different types of impacts. One is based on how many tokens we have, there might be a consequence on the latency of our application. But also, if we're running against a cloud inference service, the number of tokens will determine how much we're going to pay for that request. In this case, it's 0 because I'm running everything locally, which is really, really convenient. So all these services, as I said, have been running locally. I didn't start them manually. Whenever I start the application, I get them all. I can show you here, I have containers for Phoenix, for PG Vector. That's a PostgreSQL variant for working with AI. We can see Dockling. And as you can see here, there is no Ollama. There is no Ollama because I have Ollama running natively on my laptop, which runs better because it has direct access to the GPU. So whenever a native service is detected, and I have Ollama running here, then a container is not started. If I don't have the native Ollama, then I would also get the container. But it's much more performant having it running natively. So that's quite convenient. All of this is enabled by a couple of dependency in here. There is the Arconia OpenTelemetry Spring Boot starter that provides everything needed for a unified observability solution in Spring Boot based on Micrometer and OpenTelemetry. And now, because I'm using Phoenix, Phoenix relies on a specific standard set of conventions for naming metrics, attributes, traces. So I also added the specific Open Inference Semantic Conventions library. This is the Open Inference spec that the Phoenix platform uses. It's an optional dependency, so there can be different conversions your AI platform uses. So based on that, you can switch the naming to adapt it better to that specific platform. All right. Now, we have a contextual problem fetching data from a search engine. So how can we solve it? First of all, I want to get rid of the context. I don't want to provide it myself manually. So instead, I want the application to take care of that. So as a user, I ask my question, and then I want the application to augment my prompt with all the relevant context. This pattern is what we call Retrieval-Augmented Generation. And where does the context come from? Well, there can be multiple sources for getting the data necessary for the model to answer the question. In this case, we saw an example with a search engine. So let's continue with that example. We want to augment the prompt automatically from within our application. We can send an HTTP call to a search engine, retrieve the results. That's exactly the same that I have done manually. And then including the search results into the prompt next to my question. So the model, once receiving the request down here, will get both my original question and all the context that is needed to answer that question. How can we obtain that? Let's start looking at the code. In Spring AI, we have a concept called the chat client. That's our entry point to interact with the chat model. At the very bare minimum, we can define a prompt. Like in this case, I have a simple input, then I call the model and I return the content. But we can elaborate more based on our requirements. For example, sometimes we want to provide some instructions to the model on how to answer. So we can make the prompt a bit more elaborated. So we could specify a system message and the user message. So we can capture the question that comes from the user, but also provide some instructions to the model here. So we could say you were a helpful assistant and whatever. In this case, we won't work with that. We'll just pass this user input. But now we want to enhance this input. We want to augment the prompt with additional information fetched from a search engine. The hook provided by Chat Client for doing that is something called advisors. Let me do it here. Now, advisors are interceptors. Whenever we send a request to a chat model, an advisor will intercept that request and lets us perform some manipulation and operations on that prompt before we send it to the model. There are multiple types of advisors built into Spring AI framework. You can also implement your own. In this case, I'm going to use the Retrieval-Augmented Advisor. This is out of the box in Spring AI. And this is the advisor that lets us implement different types of patterns about Retrieval-Augmented Generation, or RAG. And we said that we want to retrieve some context. We're going to do it from a search engine. So I can use a search engine document retriever. This will perform an HTTP call. Internally, it's relying on the Spring Framework's REST client. So simple HTTP call. We can specify the results, let's say 10, and that's it. So what happens now is that whenever I ask a question to the model, this advisor will intercept the request. It will send an HTTP call to a search engine. It will get back the results, put all the results in the prompt, and then call the model. This is something I implemented, this search engine document retriever, using a Tabili search engine. So it's very simple. I'm using REST client to call the Tabili API. I'm passing a query and getting back the results. All right, let's have a look at the result now. Let's see how it behaves. So I'm expecting to get somewhat the same result from what I obtained earlier manually, but now everything is happening for me under the hood, controlled by the application. All right, let's ask, when is J Champions Conference 2026 taking place? Now it's going to take a little bit more because before calling the model, which runs locally, it needs to call the search engine. So let's see. Is it correct? It seems correct. It's starting today, the conference. Perfect. Now, I'm getting the same result, but I didn't have to provide the context myself. So we have observability configured. So let's verify what happened under the hood. So I have my chat client again. No, that's not it. That's the one. So we have the chat client once again, but now we have an extra step, which is called retrieval augmentation. Let me zoom in a bit. So this retrieval augmentation advisor will make sure to retrieve that context dynamically from a search engine. And when we call the model, we can see that the prompt looks very different from our original question. We can see that it says context information is below, and we have the 10 top results from the search engine. That's a lot of information in there. And at the end, we get this instruction for the model. Given the context information and no prior knowledge, answer the query. When is the conference taking place? So all of this is taken care for us from Spring AI through that retrieval augmentation advisor. This is a default prompt that is used to augment our question, but of course you can always customize it and provide your own instructions. And then we get the answer back that we also saw in the chatbot. Great. It's worth noticing that now we are getting, well, some slow request because we have this extra latency of calling the model, calling the search engine, besides calling the model. So we need to consider this when we design these types of application, because we are going to start adding more and more blocks to our application, and every step will add to the overall latency. So we won't have time today to look into that aspect, but we need to consider the usability of the solution and the user experience as well. All right. Now that we have this setup, we're retrieving information from the search engine, we can generalize the pattern. This is called sequential retrieval-augmented generation. What we do is we add a block, an operation before the generation step, which is the retrieval operation, so that instead of passing the original query to the generation step and to the model, we want to augment it first. And we can augment it with context from different sources. So in my example, I use the search engine, but we can also integrate it with our own data. Now, there is a problem. Our own data could be available in very different formats. We might have different PDF documents images, audio files, PowerPoint presentations, spreadsheets, or we might have screenshots, or we might have photos of handwritten documents even. So all of these different types of documents, we need somehow to extract all this information so that we can provide the large language model with a uniform and coherent body of text, body of content. It could also be image, it could be other types of content, but it needs to be somewhat coherent. But typically all our data that we want to integrate, they are not all the same. So we need to start designing what is called an ingestion pipeline. We need to prepare all our data in order to be used in the context of a Gen AI application. Spring AI provides 3 different APIs called Document Reader, Document Transformer, and Document Writer. That's very convenient names, very expressive. But what we need to do is basically reading content from different types of documents. Optionally, we can transform the documents. For example, if we have a huge PDF documents, we might want to split it into smaller chunks. And finally, we write it in a data store. Now, this data store, we don't want to write the document as is, all the text, image, whatever is it that we want to store. Because the large language model needs a different way to know what is relevant based on our question. So we don't store just the documents, but we also want to store a representation of the document that represents the meaning of the document itself. That's what we call embedding. Embedding are multi-dimension numerical vectors. So there are a bunch of numbers that represent the meaning of different content. We do that through a dedicated machine learning model that is called an embedding model. Now, since we need to deal with different types of documents, the implementation of this ingestion pipeline can be quite complicated. In Spring AI, we have different document readers available based on the type of documents you have. But I would like to show you a different approach using Docklink. With Docklink, we can pass multiple types of files, even audio or images, and Docklink has the power, using very specialized machine learning models, to convert all that information into a unified, coherent format, which is called a Docklink document. So we don't need to spend time implementing different types of pipelines based on the type of documents or different transformation operations, because Docklink is already designed to process different types of documents, different formats, and give us already a result which can be used in the context of a generative AI application. Docklink is an open source project started at the IBM Zurich. It was later donated to the Linux Foundation. It's a very successful open source project. It's written in Python. So if you have a Python application, you can use Docklink as a library. However, Docklink is also available to be run as a service that you can call through an HTTP API. And that's great for us working with Java, because it means we can call that API from our Java application. Now, we could do it at a very low level using maybe the JDK HTTP client, but a few months ago, we started an official Docklink Java project with a Docklink Java SDK that we can use to integrate with Docklink. So we got together with also fellow Java champions, Eric Andrea and Alex Soto. We've been working on this project. We are the maintainers of the project. And the goal is to have a common Java API and client that we can use across different types of frameworks and tech stacks within the Java ecosystem. So we have a portable API that we can use it. And then we have implementation. For example, Eric and Alex are working on the Quarkus Docklink integration, and I've been working on the Spring Boot integration. But we all share the same common Docklink API and client. So that's really great. It's all open source. I have a link there if you'd like to learn more about the project and maybe contribute to it. But now I want to show you how it works. So what is Docklink capable of doing? And I'll start with a simple example here. I have a very, very basic Java application with Spring Boot. I have the Arconia Docklink Spring Boot starter and the dev services for Docklink. So it means I don't have to run Docklink separately. It's part of the application flow. And here I have a standard Spring Boot application. And what I'm doing is using a docling serve API. With this object, I can build a request and ask docling, in this case, to convert my HTTP document. This is a link to the docling Java documentation into Markdown in this case. Now, all this code, now I'm using it in Spring Boot, but it's portable. As I said, the goal was to have a common API, so the same code works in Quarkus, works in plain Java. We have a nice portable model that we can use across all Java applications to call docling. Let's run it now. So we expect to see the Markdown conversion of that page in the console. I'm using JBang here. I really like JBang. All right, the application is running, is calling docling, and there it is. We have the Markdown representation back. We can see we have code blocks, they are formatted correctly. We have some links that also seem to be formatted correctly in Markdown. Great. Now, this is the foundation of our ingestion pipeline in Spring AI for this example, because now we can ingest any type of data, PDF, XML files, spreadsheets, I don't know, even audio files or images. And we don't need to worry about that because that's all handled and treated in a uniform way by docling. So how can we integrate that with Spring AI? I built an integration for that as well. So besides using docling, as I showed now, so directly to convert documents, we also have an integration with Spring AI. So we can integrate docling with our ingestion pipeline in our Spring AI application. So let's see how it works. I have my docling ingestion pipeline here. So first of all, I have here two files. They are two bedtime stories, story 1 and story 2. I have a Markdown file and the PDF files. I can show you they are in here. They are short stories about different characters. And I want to ingest them in the application so I can start asking questions about these stories. There are two files available in the class path. So what I can do is calling the docling document reader. Under the hood, it will use the docling serve API I just showed you. I pass the files I want to convert, some metadata, and then I obtain the representation as document objects. This document object, this is an API from Spring AI. So it's a way to encapsulate different types of content and metadata. All this content will later be used to be stored in the vector store. But before doing that, I also want to ingest some web pages. So I have here two articles I wrote about docling and Java. So I'm going to ingest them as well. So it doesn't have to be files you have on your file system. You can also fetch them from an HTTP source. I also specify some metadata, and that's it. In the end, I'm adding them all to the vector store. This is also an API from Spring AI. And under the hood, the vector store will use an embedding model in order to convert the documents into embeddings and then storing them in the database. All right. Now that we have all the documents in there, we can update our RAG example so that instead of retrieving documents from a search engine, we can retrieve them from a vector store. So I'm going to replace the search engine document retriever with a vector store document retriever, like this. We need a vector store, of course. I can specify additional parameters, for example, the similarity threshold, let's say 0.75. We are doing a similarity-based operation here. So we are not searching by keyword, but we are searching by the meaning of the text, thanks to this embedding representation we stored in the database. All right. Now let me update the application. I think that's it. We have all the documents ingested. So let's go here to the application and ask a new question. Now we'll ask a question about one of the stories. For example, I can ask, where are Lucio and Baloso going on an adventure? Let's see. Okay, they went on an adventure around the Italian Alps. Perfect. That's correct. Now, we have a nice way to integrate with a vector store. right? So it's the same approach as before. We have an advisor, we are augmenting the context. This time we are fetching from a vector store using a semantic search operation. And that's already a nice foundation for enabling us to ask questions about different types of documents. But there might be some challenges. For example, let me refresh the page. I showed you earlier, these stories are all written in English, and they are converted to embeddings using a very tiny embedding model that only knows about English. So whenever you perform a semantic search, searching for text related to your question, it will only return some results if the question is in English. What happens if I ask the question in Danish? For example, I can ask, hvor Lucio o Baloso rejste hen. So I ask in Danish, and we can see that it can answer in Danish. Now, what happens here? This is really interesting. Now, the embedding model is key to know what languages we can understand. Now, if the embedding model only knows about English, it will not return any answer. However, we can enable our application to understand Danish and even answer in Danish by using a chat model that can understand Danish. So the way that I do it, and I was probably on the wrong page, but the way that I do it is introducing a block here called a query transformer. So before we get to retrieve all the context from the vector store, we can also perform some preliminary operation. So we can use a translation query transformer. And this one will ensure that the question is in English. So I know that if my embedding model is tailored to only understand English, I want to make sure the question is always in English. If it's already in English, I just move on. If it's not, I want to use a chat client builder here so that a chat model can be called in order to translate the query into English. So at that point, we can retrieve the right context information and then get back the content. What else can we do? This is an important step for making sure the question is in the right format. Sometimes we ask questions that assume some previous knowledge. So there are certain words, certain terms that we use, even RAG itself. RAG, in our case, means Retrieval-Augmented Generation, but in other contexts, it might mean something else. So sometimes we want to, or we need to rewrite and transform a bit the original question in order to maximize the chances of getting a good result from the model. So whenever we are in that situation, what we can do is adding a query transformer for that, and we can chain multiple ones. They are executed in sequence. So we can add a rewrite query transformer that will make sure that, in this case, we're using a vector store, that our query is well formatted, not for a web search engine. In this case, it's for a vector store. Once again, it will use a chat model to perform that. Now, I'm using this clone operation here because I have auto-wired a chat client builder, and this one is mutable, so I don't want to mess up since I'm using it to build different types of chat clients. Whenever I want to build a new one, I'm getting a copy. That's why I'm doing this. Anyway, I have now a rewrite step where I can rewrite my query dynamically if needed. All these operations are part of a concept that move forward compared to the basic RAG. So let's have a look at the slides here. So we have this sequential RAG that I showed earlier, where we have the retrieval step and the generation step. But now we want to maximize the efficiency and performance of the retrieval step. And we can do that by introducing a new step called pre-retrieval. So in this pre-retrieval stage, we can take the original query and we can make some modifications to improve the retrieval. So this transformation is key for retrieving the right context, because it's not necessarily true that the context we retrieve is actually useful or relevant for the model to answer. And sometimes we are getting back some relevant information, mixed with other non-relevant information that might create some noise. It might be too much information. We have problems with the lost in the middle issue, where the model gives more weight to the content that is at the beginning and at the end. If we have a very long text that we retrieve from a vector store, the model might not capture the right information to give us an answer. So sometimes we might need to perform some post-processing on the context that we retrieve. So that's what we call post-retrieval phase. For example, earlier I called a search engine under the hood that returned the top 10 results in order to answer the question, when is the conference taking place? Now, since I still have this one, so if we have a look at the context that we provided, if you remember, I've been scrolling a lot, like all we need is the date, but we're passing the full body of the top 10 results from the search engine. There's so much information in there that really is not needed to answer the question. So what can we do? Instead of sending this whole thing to the model, which also increases the latency and the processing time, because the model needs to process the entire content that I'm sending, I can add a post-retrieval phase. So let me remove this for clarity. So after the document retrieval phase, I can add a document post-processor phase. For example, in the case of the search engine, I'm getting way too much content that is not needed for the question that I asked. So instead of sending all of that, I can use this compression document post-processor. So I'm compressing all the information, leaving only what is relevant for the question. Once again, we are using a chat client here to provide that. Now, you can also customize the prompt. Let me show you what it's doing. Given the following context, your task is to synthesize a compressed version of the context that is relevant to answer the input query, reducing noise and redundancy. All these steps, typically, we run them on smaller models, even running on premises, so that we can go through these steps very quickly, getting all the context needed, and keep the big model for the final question. That's also a very good idea in case you use a cloud platform for running your large language models. There might be cases where you have problems with the data privacy, because there is probably some information you don't or you can't share with the cloud provider. So what you can do is defining a document post-processor phase here, using a local chat model, like I'm doing now with Ollama, for example, so that you can filter out, perhaps implement some logic to filter out any information that you're not authorized to share with the cloud provider. So it's key here to be able to perform that operation locally or on premises, of course. And then we can use and leverage the big power of the big models at the end of the chain. So this is a very nice workflow that gives us a lot of flexibility. That's why it's called a modular RAG architecture. We have all these building blocks that we can chain and put together. We have some of them that are some implementation available in the Spring AI project itself. Most of these that I'm using here, they are out of the box, but you can also implement your own. So you can adopt different types of strategies based on your specific use case. All right. Now we are improving on this, but we are very close to getting to more problems. Sometimes we have formulated the question in a way that might not get us the best results. It might have happened to you that you try to make a search through a search engine with certain keywords, and that didn't work, and you try with different combinations in order to see if you would get better results. We could use the same approach if we have a situation where that becomes a problem, also when asking questions. So instead of transforming a single query, we can generate different variants of the query. So we can try out with different syntax, different terminology, and try to retrieve context for each of them. Then we can join all the context retrieved, and finally, we can pass all of it to the chat model at the end. By doing this, we can enable retrieving some context that might not always be available based on how you formulate the question. And here we are getting beyond the sequential RAG that we've been working with so far. We are branching out, so we are getting a more complex workflow. And Spring AI supports these too. So what we have here, let me remove the post-processor. So document retriever is the basic building block. Everything else is optional. And in this case, I want to add a query transformer. In particular, not the transformer, it's a query expander. So I have a multi-query expander that can generate multiple variances of the same query. It's using a chat model once again. And we can decide whether to include the original version or not, and how many variances we want. Maybe 3. So what does it do? Let me show you. So the default prompt says you are an expert at information retrieval. Your task is to generate a number of different versions of the given query. That's it. All of these components are fully customizable. So for each of the components I showed so far, you are always free to pass your own prompt template so that you can customize it, maybe use a different format or even a different language. Maybe you're working with a model that works with a different language than English, then you can translate all these prompts as well. All right. This, in our case, we are working with very simple queries, so we probably won't see much of a difference. But when we start dealing with a very big document basis, maybe a knowledge base in a company about your product, about your processes, this might become quite handy. At this point, I need to point out something though. I have been building this method here with the chat client, but every time I've been deleting the previous things, and at the end of the day, I still have only one possibility for my chatbot. Either I'm retrieving from a vector store, or I'm retrieving from a search engine, or I'm calling directly a large language model. Because now, if I go and try to ask a generic question, for example, I could ask, what is Java? Answer in one sentence. That's not something that is contained in my knowledge base. And then the answer is, I'm sorry, I don't have information on the topic you're asking about. That's because the Retrieval Augmentation Advisor, by default, it blocks any question that is not relevant to the given knowledge base. But then this is unrealistic. In a real application, I want to use the same interface and be able to ask questions about multiple different topics. So we need to start adding some kind of routing. We need to start supporting different paths. So if we introduce a router, then we can design different execution paths based on the question. So we might go to retrieve things from a search engine or from a vector store, or maybe even ask a model directly. We could do that, but this is very fixed static configuration. So we would like to make this a bit more dynamic so that the model itself can figure out where to go and dynamically route the request to the given target. So in order to do that, we need to move away or generalize a bit this setup. So right now we've been talking about Retrieval-Augmented Generation, and that solves one specific problem. But if we want to start integrating our application, our models with different APIs, different functionality at the same time, we need to go one step forward. So we need to start talking about tools. Now with RAG, we augment a prompt retrieving text or generic content from some source. With tools, what we're doing is we are telling the model which APIs we have available to call in our application. So we could tell the model, hey, we have available a call to a search engine, a call to a vector store, a call to the database, a call to this Java method that I have defined in this service class. And then the model can dynamically figure out which one is relevant based on the question. So we don't have to pre-compute the execution path and programmatically write in code that we want to go in one direction or the other, but we use the model to make the decision. So what happens? We send a request to the model. The model will respond with a tool called request. So it will request the application to execute a tool. In Java, that would mean typically calling a Java method. So our application will invoke a Java method. It will capture the result of the Java method call, send it back to the model, and then we get the answer back. So this pattern here enables much more sophisticated scenarios. So we're going even beyond retrieval-augmented generation. In particular, we can start talking about agentic RAG, because all those bits of logic we've been working with so far, we have the RAG workflow for the search engine, we have the RAG workflow for the vector store. They can be defined as tools, as APIs that can be called if and when needed. So we introduced the concept of an agent, which in this case, it's really a large language model that can make decisions about which tools to call based on the query. So it might choose one of our tools or might just choose to answer based on the information that the large language model itself was trained with. How do we do this? It's very simple in Spring AI. We can, where is the mouse? Here. So I can remove all of this, and I will keep this call as my agent. So now this chat client will act as my agent. It will get the user input, but then I don't implement any logic to retrieve context. Instead, I define all that logic as tools, and I have already done that. Let me show you. I have a tools class in here, where for each of those RAG workflows I've been presenting until now, I define them in a method. For example, I have here a story retriever, and I marked it as a tool. So in the method, I still have a chat client. I have a retrieval augmentation advisor that fetches from a vector store any data relevant to one of the stories. So you can see here the metadata I defined at the beginning in the ingestion pipeline. I can use that information to filter the results. And the key part here is this tool annotation. This tool annotation will tell Spring AI that we can make this method available for the model to call. The description here is extremely important because it's the piece of information that the model will use to decide whether to call this tool. So here I'm saying retrieve information about stories and adventures taking place in the world of these characters. Great. And then I have a different tool to fetch information. I ingested some pages, some web pages about Orconia, about Dockling and Java. So I have a different tool for that. It's also a RAG workflow, but now it's encapsulated. So I have two different RAG workflows, and they are both marked as tools. And I even have a tool for retrieving from a web search engine. So I have three tools now, and I can pass them to my agent. So my chat client can be expanded with tools. Now these tools, let me go back. So this tools class is a Spring component, standard Spring component. So I can auto-wire it and pass it to my chat client. That's what I'm doing here. So now whenever we ask a question to the model will know about our tools and will decide whether it makes sense to call any of them. That's all done dynamically. The model makes the decision here. So I don't have a workflow with predefined execution path. Let's give it a try. So let's start asking a question about where do Lucio and Paloso go on an adventure? So here I expect that the tool about the story retrieval is called. Let's see. Perfect. We got the right answer. And let's double check in the monitoring. Let's see. Perfect. So we can see we have a first call to the model. We are asking where do Lucio and Paloso go on an adventure? And next to the question, we are also passing all the metadata about the tools that are available. So this is all handled for us under the hood by Spring AI. So we just annotate the Java methods with the tool annotation, and then Spring AI takes care of generating all this information. This is necessary for the model to know two main things. First, what is the tool for? And we have the description down here. And second, how to call that tool, because the tool or the model will tell the application how to call the tool. So with which arguments. We said it's a method call. So the method has some arguments, so the model needs to format those arguments correctly. That's why we're specifying here a JSON schema. In this case, we only need to pass a query, so it's one field. And then we can see the tool called story retriever is called. We can see the input, that's our original input, and the method argument that we are passing, and then we get the output. Finally, we can see that we have a final call to the model where we pass both the original question and the result from the tool call. So all the contextual information about Lucio and Baloso. And in the end, the model knows how to answer. Now, one more test. Let's see if I ask questions about, let's see, what can we ask? What is, yeah, so maybe the search engine. Let's ask again, when is the J Champions Conference taking place in 2026? Now I expect that the other tool, the search tool, is called. And we can tell because it's taking more time calling that API. Let's see, perfect. Seems correct. Let's verify that's what's happening. Here it is. Yes, web search retriever tool call, perfect. Now we can add more and more tools. Every Java method can be a tool, but in the ecosystem, we also have a standard way to exchange or to provide tools across different tech stacks, different programming languages and frameworks. That's called MCP, Model Context Protocol. So how does it work? So we have a generalization of agents. Now we are retrieving content, but we can do much more than that because these tools can retrieve information, but they can also perform operation. So you can maybe update the state somewhere in the database. You can perform different types of actions. But it's all related to tools that you have available in your application. So in my case, for example, I implemented how to call a search engine. But with MCP, we can call any kind of APIs, even external to our application. And we can do it through this model context protocol. Spring AI supports that through an MCP client. It's the same tool call approach as before. The main difference is that the tools are not things that we define or that we implement in our application, but they are implemented by other parties. That's what we call MCP servers. So for example, the search engine I used, Tabili, they also offer an MCP server. So there is an MCP server that I could integrate in my application to perform searches through their API without being me implementing the HTTP call. So in the tools that I have available here, I can actually remove the final one. So this web search retriever tool, I can remove it. Let me comment it out. And in its place, I'm going to use the Tabili official MCP server. I can configure it in different ways, but a convenient way is through properties. So I have Spring AI properties for an MCP clients. I name it Tabili search, and I'm referring, in this case, it's a Node.js MCP server from Tabili itself. I pass my API key, and that's it. So now that I have this MCP tool configured, I need to pass it to the application. That's the final part. So these tools will only include my own APIs, but now I want to provide additional tools. So I have already auto-wired a tool callback provider for MCP. This is something that Spring AI auto-configures for you. So now I will have available my own tools and tools that comes through the MCP protocols. In this case, just the search tools. Let's see if we can achieve the same result. All right, now I'm going to ask, when is J Champions Conference taking place? Now, the result is expected to be the same. However, because we are going through the extra indirection layer, sometimes it might be slower. So we have the answer that is correct. Perfect. So we can also double check in the platform here. Yes. So we can see that we are calling a tabuli search tool. There is a final thing I want to mention here. Now, it's very easy and convenient to add more and more MCP tools or MCP servers integrated into your application, but each of these MCP server can come with lots of different tools. Like in this case, I have just replaced my own single tool that I implemented for tabuli, but if we look here, this MCP server actually provides 4 different tools. So I have my 2 tools that comes from my Java application, but then tabuli provide a tabuli search tool, tabuli extract, tabuli crawl, and tabuli map. Now, the more MCP clients I add to my application, the more tools will be there. At some point, you can easily end up having 100 different tools that every time you call the model, you have to include. And that's really not efficient. It's not just a performance issue or a latency issue, but if you're using a cloud platform, it also means that you're paying a lot for the tokens to represent or to exchange information that most of the times is useless. Because for each question you ask, you probably only need a few different tools. So I want to mention a recent project from the Spring AI community. The Spring AI community is a project which is let me see, Spring AI community. You can find it on GitHub and feel free to join. It's where we host lots of different projects from the community that are not yet part of Spring AI core. There's lots of different projects also from the same maintainers of Spring AI. One of them is the Spring AI tool, search tool from Christian. With this tool, you can actually make sure that you only include relevant tools every time you send a request to the model. So here I can actually add an advisor with a search tool called advisor that comes from that project. And this one will search among all the tools that I'm passing here to my agent. It will only maintain the tools that are relevant based on the question. So it will make sure that even if you have 100, 200 tools all together, the model will only receive the ones that are relevant. So that's something to keep in mind because it's very easy to get started and integrated with more and more MCP servers, but very soon it will become a problem. All right, that was the final thing I wanted to share. Thank you very much for joining this session. You'll find all the source code on GitHub. And if you have any question, I have time and feel free to ask.
Thank you so much, Thomas. And I have also just invite our viewers, if they have questions, to ask on the chat. But I so far have not seen anything yet. And then again, folks, if you want to join the next session, it's going to start shortly. But Thomas can be here to answer any questions which you may have. So.
Yes. Otherwise, you'll find me on Blue Sky or LinkedIn. I'm always happy to chat about this topic. So feel free to reach out there or on GitHub directly. And I'll be happy to discuss these topics if you don't have questions now.
That's right. I want to post this comment here. All sessions will be available till the end of time. So folks, if you miss anything, please go back to the recording.
Yeah, I can see there's a question. Given that we handle sensitive data, is it recommended to use an external MCP server or should we host it internally for security reasons? Yeah, that's a very good question. So that's probably the major risk I see with this type of application. It's very convenient to call MCP servers hosted remotely or calling these cloud platforms offering different types of inference services and AI capabilities, but it's really a big risk when it comes to private data. So my recommendation is always to consider that aspect. There are MCP servers that you can host yourself, but sometimes these MCP servers, at least the most convenient ones I found in terms of remote connections, are a replacement to existing HTTP APIs. For example, in this search engine, no matter if I use an MCP client or an HTTP call directly, I will still be sending sensitive data if I have sensitive data in the query to a search engine. So it's important when building these kind of workflows to consider that aspect. And there are ways we can guard our application from sending sensitive data. For example, you can add guardrails. Using the advisor mechanism, you can have input guardrails and output guardrails so that you can filter out sensitive data in case you are about to call an external service. But I think at this point, there are very many possibilities to run many of these things on premises. Now, all the examples, as I mentioned earlier, are running on my local machine, so I don't have any problem with sensitive data. The only external connection point was actually the search engine, because I don't have a web search engine running on my local machine. But there are many different models for doing that. One of the reasons why I like Docklink is because Docklink performs the document conversion not based on large language models, but it's based on very tailored and specialized machine learning models that run fully locally. So you can process any kind of document in your company without being worried about sharing sensitive data. So it all remains on premises. And then if you need to call an external system and you're afraid of sensitive data, I really, really, really recommend putting up some guardrails, some filters, and making sure that doesn't happen. But MCP servers are definitely available to be run also locally. So if it's something that works on premises, you can definitely do that. I hope that answered the question.
Thank you. Okay.
Yes, seems like that's it. But I want to thank you all again, and thank you, Mary, for hosting this, and thank you also to the organizers of the conference.
Thank you. Thank you so much. And and Thomas can always be found, based on the handle here he has on screen, so you can reach out to him afterwards as well. So with that, I think we'll end this particular stream. And folks, please head on to the next session, and it's with Andre. So yeah, please join us there. And thank you again, Thomas. Thank you to everyone, wherever you are. Have a great day or evening or afternoon or night. Yeah. Okay. Thank you. Thank you. Okay. Okay, cool. I'm going to end the stream. Wait. Okay.